Welcome to lecture 4A. We're going to talk a lot about acid and base chemistry in today's lecture. So we're going to start out talking about something called Bronsted-Lowry acid-base theory. Now, if we go back, a couple thousand, 3,000 years, we've known what acids and bases were, or at least I should say we had an idea of something that was an acid and something that was a base. Long ago, we had no type of elemental analysis, and so as a result, acids and bases were classified based on what they reacted with and what types of products they may have had. So one of the things that people noted a very long time ago is that reactive acids tended to contain oxygen. And if we look at a lot of our acids today, are highly reactive acids, that in fact is true. But then later it was noticed that there were other acids that were also very reactive that contained no oxygen, but did contain hydrogen and halogens. And so we called those hydrogen halides. And your halides or halogens are elements from group 7. It was Svante Arrhenius, who we just saw in the last week's lecture, dealing with the Arrhenius equation. He also did a lot of work with acids and bases, and he was the first to notice that compounds with acid properties generally contained hydrogen, and basic compounds contained hydroxide, OH-. And so he set out to really classify acids and bases by their chemical structure and their chemical makeup, rather than by their behavior in when reacting with something. The problem is that the Arrhenius theory of acids and bases that said things with H pluses made acids and things with OH minuses made bases, it had a difficult time describing why compounds such as ammonia or any of the amino acids had acid or base properties. They didn't behave according to the Arrhenius acid-base theory. But the Arrhenius acid-base theory was a very good start. And then some years later, a new theory came about called the Bronsted-Lowry theory. Now, those two gentlemen did not work on the theory together. They actually came up with two very similar theories independently right around the same time, and so they're given joint credit for their discovery, and so we very frequently call it Bronsted-Lowry theory. So this new theory, Bronsted-Lowry theory, still needed to support the idea of Arrhenius theory, because things with H's were in fact acids, things with OH minuses are in fact bases. But we had to then also include in this new theory other compounds that had acid and base properties that didn't fit in the Arrhenius theory. And so really I like to think of it as a bigger circle. It encompassed more compounds with acid and base properties. So Bronsted-Lowry set out, rather than looking at the chemical makeup of a compound, instead they started looking at what was the compound's behavior during the course of a reaction. So Bronsted-Lowry acids are defined as compounds that donate a proton, and a proton is just an H plus ion. So they donate a proton during a reaction, and a Bronsted-Lowry base is defined as a compound that accepts a proton during that reaction. So we have proton donors and we have proton acceptors, our acids and our bases. So notice, like I mentioned earlier, that the definition has no mention to a substance's intrinsic chemical properties. Instead, it looks at its behavior during a very specific chemical reaction. So let's look at this kind of in action. One of the things that the Bronsted-Lowry theory means is that you cannot strictly define something as an acid or a base outside of a reaction. Now, I know that we do that a lot because there are some compounds that pretty much always behave as an acid or always behave as a base. But there are other compounds where you do have to look at the reaction it's involved in to see, is it behaving as an acid or is it behaving as a base? Let's look at an example here. CH3CO2H. So this is acetic acid. When mixed with water, it forms vinegar. So we're very familiar with this acid. When we put this acid in water, it does in fact donate an H plus to the water, and it gives us something called an acetate ion and a hydronium ion. Now, hydronium ion is that H3O plus. Now, if we want to classify what is an acid and what is a base, we have to look at what donated an H plus and what accepted an H plus. So if we look at our acetic acid here, notice that it's missing an H plus and going from reactants to products. We're missing that H right there. It's no longer there. Where did it go? It went to the water, and the water became H3O plus. So now we have an additional H and we have an additional plus for the H plus. So the CH3CO2H donated an H plus. That makes it a Bronsted-Lowry acid in this reaction. And the water behaved as a base because it accepted an H plus. Now, we don't normally think of water as a base or as an acid. But again, that's a lot of times thinking in terms of the Arrhenius theory. With Bronsted-Lowry theory, we have to see what did it do during the course of the reaction. And here it accepted an H plus, so we have to classify it as a base. Now notice I also put labels on the products there, conjugate base and conjugate acids. We're going to talk about conjugates a little bit later in the lecture, but I wanted to throw out those terms now. Notice that your Bronsted-Lowry acids and bases are in the reactants and your conjugates are in the products. So, as we mentioned, what lost an H, what gained an H. That's how you identify what the Bronsted-Lowry acid and what the Bronsted-Lowry base is in an acid-base reaction. So let's look at ammonia, because this was one of the primary compounds, a very common compound, even in the 1800s, that really caused Bronsted-Lowry theory to be developed, because it has very clear basic properties, but it did not fit into the Arrhenius acid-base theory. Bronsted-Lowry theory actually has a way of describing why ammonia has base properties. So let's take a look at that. What happens when we put NH3 in water? Well, it turns out we get NH4 plus OH minus. So even though NH3 has no OH in it, when it goes into water, it becomes a source of OH minus because it takes an H plus away from the water. And so we can classify these a little bit better. So here we have our NH3. So this is going to now be our base because it took an H away from water. And our water now we can classify as an acid because it donated an H plus. It gave an H plus away. So we see that our NH3 and NH4 are linked together. Our H2O and OH minus are linked together. Whenever we're doing these types of reactions, when we're looking at Bronsted-Lowry acids and bases, or conjugate acids, conjugate bases, we generally look at only one single H plus being transferred at a time. So notice we go from NH3 to NH4 plus. We go from H2O to OH minus. One of the easiest ways to identify what our conjugate pairs are, in other words, the base and the conjugate acid, or the acid and the conjugate base, those two compounds are going to be linked together because they differ by only a single H plus in their chemical formula. Now, notice when we look at water, when we were looking at the acetic acid problem, we classified water as a base because it accepted an H plus, and here we've classified water as an acid because it donated an H plus. Before this lecture, you may have never seen water classified as an acid or a base. We've always talked about water being neutral. But again, Bronsted-Lowry theory doesn't look at the chemical formula, it looks at how does it behave in a reaction. And we can now see that water can behave as either an acid or a base depending on the type of reaction it's involved in. And when you have a substance that does that very commonly, we refer to that compound as amphiprotic, which means it can go both ways with protons. Kind of like an amphibian means both land and water. Amphiprotic means it can donate or accept protons. Oh, there's our base acid, conjugate base. That should have come up a little earlier, sorry. So let's talk about this idea of conjugates. So conjugate acids and bases are compounds that have the acid and base properties in the reverse reaction. Remember I mentioned that your acid and base for the reaction are your reactants, and the conjugates are always the products. Well, the products of a reaction, as you write it, are the reactants for the reverse reaction, a reaction going the opposite direction. We talked about that with equilibrium. So in our first equilibrium that we saw with acetic acid, your acetic acid and your acetate ion make up a conjugate pair. Your water and hydronium make up a conjugate pair. And like I mentioned earlier, also the compounds that form that conjugate pair differ by only a single H+. It must always be a single H+. If they differ by more than a single H+, then they are not conjugates. They will actually share a common conjugate in between them. So let's look at strong acids. We've got lots of different types of acids and bases. You may have heard of strong acids, weak acids, strong bases, weak bases. So what does this idea of strong mean? Well, let's look at strong acids. So if we look at HCl, hydrochloric acid, very common strong acid, one of the most frequently produced chemicals in the entire world. When we put that into water, it becomes hydronium ion and Cl-. So there we see the HCl acting as an acid. We see the water acting as a base. The water becomes hydronium. The HCl just becomes the Cl-. Now notice when I wrote out that reaction, I did not use an equilibrium symbol. I just have a single arrow going to the right. Now, why did I not use an equilibrium symbol? Well, in reality, everything reaches a type of equilibrium. Okay, but here the equilibrium is shifted so far towards the product side that there is essentially no equilibrium. Okay, it'd be like if you had a million euros going in one direction and 10 cents going in the other direction. Essentially, everything went to one side. Same idea here. This reaction is shifted so far to the right towards the products that there really is no equilibrium, so we ignore anything that might go in the backward direction in reverse. So essentially what we have is a complete dissociation, a complete breaking apart of the HCl molecule in water. And so what that means is that if I know the concentration of HCl, I also know the concentration of H3O+. So really, if I have a jar that says that I have 1 molar HCl, what that really means is I have a molar H3O+, because the HCl is completely dissociated. But we say HCl because that was the parent chemical that went in. Another way of looking at this in terms of our conjugates is to say that the conjugate base of a strong acid is ineffective as a base. The reason that the acids and bases that we looked at previously set up in equilibrium is because we have an acid moving in the forward direction reacting with water, but it creates a conjugate acid and a conjugate base that have acid and base properties. And of course, acids and bases like to react. And so the conjugate acid and the conjugate base react as an acid and base and go back to the reactants. And so it sets up that equilibrium. So when we have a strong acid, really what that means is that the conjugate base of a strong acid is ineffective as a base. It's so ineffective that it can't even react with a hydronium ion. So that would mean that Cl-, that is our conjugate base of a strong acid, HCl, which means it's ineffective as a base. It will not react with acids. It will not react with water as far as pulling an H+ away from anything else. There are 6 main strong acids that you need to make sure that you recognize in a reaction. And the reason you want to make sure you recognize them is because they break up completely and have no equilibrium. And knowing that fact will help a lot of different times. So the 6 main strong acids are 3 of the halo acids, or hydrogen halides, HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, and then 3 what we call oxoacids, and they are H+ combined with a nitrate ion, a sulfate ion, and a perchlorate ion. So we have nitric acid, HNO3, sulfuric acid, H2SO4, and perchloric acid, HClO4. So we talked about strong acids. Let's look at weak acids now. Okay, so weak acids ionize just a little bit. In other words, very little of my acid actually dissociates, breaks apart, and loses that H+. And as a result, we get an equilibrium setting up in solution. So here we have our HA. This is just a generic acid. We see this very commonly when we're just talking about acids in general. So HA is just the H plus the rest of the acid is a way to think of it. Reacts with water, and it's going to form the H3O plus, and whatever is left over after the H plus is removed. This, as far as acetic acid, this would have been our acetate ion. Okay, so notice that we have our double arrow here indicating that we have an equilibrium going in a forward and reverse direction. Now, because we have an equilibrium situation, we can write an equilibrium constant, and we have a special symbol for an equilibrium constant involving a weak acid, and it is Ka. Now, the A doesn't really mean anything. This is still an equilibrium constant. We still write it as products over reactants. The little a just tells us that this is an acid dissociation constant. It just says that we have an acid reacting with water, and it's giving us H3O plus and the conjugate base of that acid. So we still write products over reactants, like I mentioned. So here we have our A minus right there, our H3O plus right there, and our HA right there. Okay, notice that I did not include the water in the equilibrium constant. And that's because water is a pure liquid, and we don't include pure liquids or pure solids in our equilibrium constants. The reason for that is because their concentration is a constant, and because their concentration is a constant, that means that that value already gets worked into the equilibrium constant. So we just leave out pure liquids or pure solids. Okay, so there's our Ka, acid ionization constant, also called an acid dissociation constant. Now, the interesting thing with our weak acids and strong acids have Kas 1,000, 10,000, 100,000, million, depends on the circumstances and on the acid, whereas weak acids have Kas typically in the 10 to the minus 3, 10 to the minus 4, 10 to the minus 6, 10 to the minus 10, very, very small values. What I find interesting is that there's really nothing in the middle. It either dissociates virtually 100% or it dissociates just a fraction of a percent. There's nothing that dissociates like 30%. It's just an interesting fact in there. But here we see several different types of weak acids and their associated Ka values. You can see that they have quite a wide range of Ka values. You have something like chlorous acid up there at the top, ClO2 with one of the larger weak acid dissociation constants, 1.1 times 10 to the minus 2. That's actually quite a high value for a weak acid. And then we see something down here like phenol, which has a Ka of 1.3 times 10 to the minus 10, which is actually very small when you think about how much product is formed. Very little product gets formed when you have an equilibrium constant that's that small. A lot of times the question I get is, are you expected to memorize these values? Good grief, no, because this is such an abbreviated table. A true table of Kas is pages long with very tiny type. So if you need a Ka for a problem, you will be given it, or you'll be given a table in order to look it up. All right, well, that finishes out our initial discussion on acids and bases. If you have any questions on any of the content, please make sure you contact me.